Good day, students. I am the venerable Zulita, student of SolidGeometry. May I introduce to you the theorem number 1. Theorem number 1 stated that two planes meet in a straight line. See in this solid, we can see that plane C intersecting the plane X. They intersect at a straight line, so their intersections form a straight line. Another example, plane C and plane B intersect at one line. Plane E and plane C intersect at this line. Plane R and plane Y intersect at this line. After knowing that the two planes meet in a straight line, let us first determine what is a plane. A plane can determine by number 1, a line and a point not on it. So let us see in this figure. This is the line R, S, this line, and a point M. Second is two intersecting lines. So line S, M, and RS. They are intersect at point S, and two parallel lines, which is SM and RP.
Good day everyone, I am Verula, student of SolidGeometry. Together with my partner, the Zulita, that discuss to you the first and the second theorem, I am going to discuss to you the third theorem. The third theorem, let's have a cube. He discussed lately that two planes intersect each other at a line. I will going to discuss that if a line perpendicular to the intersection of two intersecting lines, it is also perpendicular. This line XB is also perpendicular to the plane ABM. Inside a cube, we have a plane CAXB, and line CX intersect XB at point X. Another line PX intersect at a point of intersection between CX and XB, and PX is perpendicular to XB, CXB and XC. If we have a line perpendicular to the point of intersection of two intersecting lines, this line is perpendicular also to the plane CXB. Another theorem, the theorem number 4, explains that through a point, one and only one plane can be drawn perpendicular to a line. So, see this line AB at plane ABS. At this point A, in a line AB, one and only one plane can be drawn perpendicular to this line at this point A. So what is this plane perpendicular through AB at point A? This is the line, this is the plane ACR. Another, through a point S in a line SM, one and only one plane can be drawn perpendicular through the point S, and that is the plane AS and R. The inverse of the theorem number 4 is the theorem number 5. States that through a point, one and only one line can be drawn perpendicular to a plane. At the same cube, we have a plane RPX. Can we say that at point R, there's only one line perpendicular to it? Yes, only line SR can be drawn perpendicular to the plane RPX through point R. Another plane CXB, it said that one and only one line can be drawn perpendicular to a point C. And what line is it? Is it a line RS that can be drawn perpendicular to the line CXB only at point C? We are now down to our last theorem, the sixth theorem, solid geometry. The sixth theorem says that if an oblique line from a point meeting the plane at equal distances from the foot of the perpendicular are equal, so these lines are the oblique lines. How can we prove that these lines are equal to each other? Simply through angle side postulate. So what is this side angle side means and how we get this postulate? It is first stated that we have a perpendicular line from a plane. This plane, we have a perpendicular line like this. So we forms two triangles A, D, and F. Another triangle A, D, and F have the same common side, which is the perpendicular side. So we have this line with a common to the two triangles. Another, it is said that with an equal distance from the foot of the perpendicular. So which means this line, these two lines have their equal distance from the foot of the perpendicular. So it is congruent to each other. And the theorem says that this perpendicular line forms 90 degrees. So we have now an angle. This means we get the side and angle side postulate to prove that this AE is equal to AD.